Hello and welcome to a Libre-SOC project, Craystar Vectors for OpenPOWER. So I'm going to do this in a slightly different style of talk. We're going to use web pages online, so you can actually follow along and see these links for yourself if you wish. They're at libre-soc.org/conferences/CINECA 2021. So a brief overview of the Craystar Vectors that we're adding. OpenPOWER was picked because it's already a supercomputer style instruction set. The primary thing, there's an article online on SIGARCH, SIMD, called Harmful, which we took to heart. The typical expansion of a SIMD instruction set is enormous. You first have the operation, then you have a bit width. Now, if you note here that that's only up to 128 there, but in the case of AVX512, it's now up to 512 bits. So you've got instructions for, you start off with the operations add, multiply, whatever, and you then multiply those by bit widths that do 8, 16, 32, 64, 128, 256, and now with Intel 512. So you've now, initially you had 40 instructions. Now you've got 40 times 2, 4, 8. You get the idea. Then you have conversion instructions. Then you have some that are signed and unsigned versions of the thing. So you've multiplied by FB16, 32, 64, 128. Now you multiply by Pascal's triangle there. Signed and unsigned, you've doubled them again. But for DSPs, you double them. Well, actually, you multiply them by about 16, because you have high-low selection. So high, low, low, high. Things. So you multiply by 4. You start to see that it gets quickly out of hand. What should be 70 instructions turns easily into 1,000 or 2,000 instructions. Craystar Vectors, on the other hand, they're ridiculously short. Now, the fundamental basis of Craystar Vectors is that you have like the old x86 rep instruction. You have a prefix which says, here's your base, I'd like you to repeat it n times. And in the Craystar Vectors, you have, in the original Cray instruction set, you have an instruction called setVL, which sets your vector length. Now, the actual hardware, it's hardware agnostic. So in your program, you write programs that literally, the programmer doesn't actually need to know how long the vector really is. That the hardware tells you, it's limited to this much. But that's at runtime. That's critically important, and it's a completely different paradigm from how SIMD operates. Now, we're doing something slightly differently. It's effectively the same, and you have this for loop. So you have a scalar add, not a vector add, a scalar add that is repeated as far as the programmer is concerned, VL times, and VL vector length is dynamically selected programmable at runtime. It's not hard coded into the program source code like it is in SIMD. So once you've got that basic concept, we've then added the ability that through tagging, as it's called, to set a tag as to whether the destination is a scalar or a vector, whether the source 1 is a scalar or vector, and whether source 2 is a scalar or vector. And consequently, there's 8 possible permutations here, one of which is the original scalar add. So when all 3 of your the registers are marked as scalar, you have the original OpenPOWER v3.0b scalar add. It's quite simple. So the next bit on top of this is that you can add predication. Now, bear in mind, none of this is done by actually modifying the scalar v3.0b instructions. It's done via this context. So you've got a rep style prefix, which contains an indication of a desire that the scalar operations should be predicated, and basically that you specify a predicate value which at runtime can mask out individual operations. Right, and that's critically important for 3D workloads, vector video processing, vector process, everything. It's the fundamental basis of AMD, Intel, and NVIDIA GPUs. Now, so that if you can read about that, just search yourselves on that overview article there, Libre-SOC.org/openpower/sv/overview. Now, I want to go a bit more over this this article, which is the significance is deeply understated. Right. The more I investigate, the more I'm horrified at the effect that SIMD has had. That's not a joke. Here's your program. Thing is the standard DAXPR, double add with x times y. Y equals ax. Y brackets I equals a constant, scalar constant a times x, and you add that on. So it's the standard y equals mx plus c algorithm. All right. Now, the number of instructions, although this is for RISC-V vectors, it's exactly the same concept for any Craystar architecture. You have your setVL here, where you attempt to do 10,000 or 50,000 or a million, but the hardware says, oh, actually I've got only 4 lanes, or I've got 32 lanes, or I've got 1,000 vector lanes. It doesn't matter how many it has. It limits that the number that it's going to do to VL and puts it into a temporary variable here. Now this is important for later, right? Now, when your vector length has been set, load vector X will load VL entries into memory. Now it doesn't say that it's the way that it's done. That could be done one at a time, or it could be done if your hardware implementation gets capable that you could do an entire 512-bit wide load. But it's up to the implementation to define that thing. So there's your vector load of y. You incrementing the pointers here. Here's the actual add. Now again, it doesn't say how. In the hardware, it hasn't. In the instruction, sorry, it hasn't said I am explicitly doing 4. I am explicitly doing 8, like you have to do in SIMD. But it multiplying by the constant a, subtracting the vector length from the number that have been calculated in this iteration through this loop from your count, your n count a0, and repeat if that count a0 was non-zero. But that's it. That's all it takes. Note the complete lack of SIMD setup and teardown. Okay. All right. Here's what it looks like for MIPS. All right, and which has a 2-wide SIMD, and you had to first. There's your main loop, which if you're very lucky, you didn't overrun the thing because you actually are called for n equaled 0 or 1. Oh, here's your fringe code. Yes, you have to detect if it's a fringe here, and then if it's even you were done, and if it's it's awful. All right. I've got some illustrations later of quite how bad this gets when you go up to 512 bit, 128 bit and 512 bit thing. But you should have that sinking feeling at this point. Now, here's a really useful illustration of SIMD versus vectors. Now, on the face of it, it looks like the SIMD instruction is more efficient and completes quicker because you've got 4 loads being done at the same time, you've got 4 adds being done at the same time, 4 multiplies and 4 stores. The problem is, whereas the load, you're only doing 1 load at a time here, all right? Therefore, it completes in, it takes way longer, all right? The problem comes when you look at this and you realize that that is if it's a 64-bit load, that's 4 64-bit loads. That's 256 byte wide hitting the memory subsystem at once. And until you have, here's the kicker, because it's SIMD, until you have done all 4 loads, you cannot do the adds. Likewise, the caveat of SIMD is until you have done all the adds, you cannot do the multiplies. And correspondingly, only when all multiplies are completed can you do the stores. Here, there's only one load, one store, one load at a time, and one store. But look, they're overlapped. All right, this is called chaining. All right, and if you were to compare like for like here, you would have to do one load here, followed by another load in the second cycle, and another load in the third cycle, and another load in the fourth cycle, and only then, once you had performed all your 4 64-bit loads, could you do one row of adds. Then you get your one row of multiplies, and then you have to have store, a 64-bit store, and then another one here, and another one down here, another thing. So it's actually, if you work it out, and you're doing a like-for-like comparison of an array processor with 64-bit wide load, 64-bit wide store, you end up with much worse performance, much worse latency on the SIMD processor than you do versus the vector one. And this is something that's been completely missed. But not only that, it should be quite obvious that when you go to 256-bit wide SIMD, 512-bit wide SIMD, 1024-bit wide SIMD, the problems get worse, not better. You have to wait for the entire 512-bit data to be available before you can move on to the next thing. Whereas with the vector chaining, it's you get these inflows, a much more efficient use of resources in your hardware, and a small completion time is better, latency is lower. Now, this is so bad it's not even funny. Here's the integer version of that DAXPY version of that code. Okay, all right. It's using integer y and integer x, integer a. I compiled this for AVX512. Let me shrink this down. Here's the assembly code. It's 273 lines of assembly. Whoever thought this was a good idea? I'm confused and actually, in some ways, quite angry and embarrassed that this is how things work. If you look here, you can see what it's doing. And the reason why it has to do this is because the alignment on SIMD is often to the boundary. So you don't just have a like in that the SIGARCH article, you had a fringe thing. You have a preamble stage where you have to get up to the alignment width of the SIMD operations. And that, I believe, is what's going on here. So it's going. Have we got one item in our array that's not aligned? No. Jump over. Doing jump. You get, because it's AVX512. You get 15. I mean, I'm sort of shocked. Then you get the actual instructions of the inner loop to do the SIMD multiply, and then afterwards you have to go through the same process of same cleanup process. I mean, it's awful. But I have to say, rather embarrassingly, it's the same thing for VSX on OpenPOWER. Here's a Strinacopy implementation for IBM Power 9. It's 240 instructions. The same thing that has to be done. By contrast, here's the version that's for RISC-V. This is a Strinacopy, but literally that's it. It loads a vector of bytes. But here's one thing. Sorry, this is a set vector length for getting vectors of bytes. But here's the important thing. There is something called fail on first, which is what happens here is that the vector length is truncated to an appropriate length that the hardware, a length that the hardware deems appropriate, and that's particularly crucial. This was something that was introduced with ARM SVE2, and it makes sure that you don't overrun a page boundary. So the actual number of elements that are loaded is within the amount that the vector engine, the parallel vector engine, can deal with. And you don't have to have that logic detection for the thing, but you can't have it anyway. You don't have to have that in the inner loop. If you attempt this kind of thing in SIMD, well, you can't actually do it because you have to you have to attempt the load and then detect the page faults. That's in user space. But you can't do that. That's completely unsafe. We're adding this feature. It's called what's it called? Fail on first, but it has another one, speculative loads, as well. I think now. Next one here. I also sorry, I should have done this I've done this slightly out of order. I also did the IAXPY version in PowerPC with VSX. And again, you can see that the amount of code is extremely large compared to I think it's about 5 times larger than the RISC-V Stringer copy version. So unfortunately, to say, despite the fact that the achievement with IBM with the Power 9 and the Power 10 is absolutely fantastic, I think it just they missed a trick with vectors. Now. Currently, what we're doing is we're in the Libre-SOC team is we're doing some demonstration codecs, video codecs, and one that came out particularly interesting was the MP3 algorithm, which has this is directly from FFmpeg source code. It's called apply window function, MPADSP apply window floating point version, and this is a macro which does 8 multiply and accumulates, and then 8 multiply and subtracts. So here's the macro this does. And when you expand this out, we compile this in C for PowerPC scalar. You end up with over 400 instructions. 400 assembly instructions, because that macros end up expanding out to these massive numbers of multiplies and subtract, multiply and subtract instructions. Which is rather unfortunate. The same code for the SVP64, which we're calling it, only ends up at 80 instructions. Well, actually 100 32-bit instructions. It turns out that we vectorized multiply and accumulate, and it turned out to produce results that were too accurate. So for unit test purposes, we do them explicitly as multiply and add, multiply and add. So there's one here which is the add, and then there's the other one is subtract. Now, one of the important things about vector instruction sets is that they have what's called a MapReduce mode. So you don't find this in SIMD because everything is in lane. So how can you add things that are interlane? You can't add interlane, whereas with vector instruction sets you can. And we did a bit of a cheat in this one, is that the MapReduce mode, we're relying on the out-of-order execution of a standard scalar add. So RT is the scalar thing here, and RA is the scalar source, but it's a vector source too. And what this will do is, again, according to that simple for loop here, this simple for loop, RA equal, it's a scalar source. So all it's doing is it's adding the register B onto A continuously. Right. There's nothing special here. It's nothing explicit. It's just putting the vector engine into a special mode, which performs a sum. So yeah, really quite straightforward, and it results in a reduction in the code size of a factor of 4. When you compare it against the Intel version, which uses SSE, I think it does, it's a factor of about 6. And that's just, you just don't have, in computer science, you just don't get those kinds of savings. It's perfectly normal for in some instructions to maybe have, a factor of 10%, 5% you add some new instructions. If you get a 2 times saving in power, that's enormous for adding a particularly new concept like the multiply and accumulate system, the matrix multiply assist. As added, they're getting in power 10, they're getting 2.5 times power reduction and things, but you don't get a 4 times or a 10 times reduction in program size with associated reduction in the level 1 cache usage. So that was the first part of that. The second part, we decided to go on to looking at the at FFT, because that's part of discrete cosine transform thing. So this algorithm, the Kuei-Tukey algorithm, is particularly known because it's an in-place algorithm where you perform these butterfly swaps, and you recursively perform the thing on the left half and the right half, and then perform then you go down recursively into those two, and then you at the level that you're currently at, you do this butterfly multiply and accumulates twin multiply, add on one of them and subtract on the other, but you do an in-place overwrite of the array in your pseudocode here. So you're creating P and Q from the S values, but you overwrite at half the thing. All right. But there's two stages to this. One of them is that if you do it in completely as an in-place algorithm, you have to actually do this bit reverse, a copy of your data. So what we decided instead was to add a bit reverse load mode. It sounds confusing, but what that means is that it's a special mode, load word 0 in bit reverse mode. So if the vector length is 4, then instead of 0, 1, 2, 3, which is binary 0, 0, 0, 1, 1, 0, 1, 1, we actually load from the bit reversed version of those, which is 0, 0, 1, 0, 0, 1, 1, 1. All right, and this is one of the key problems of I think you should see some of the algorithms for doing bit reversal in a scalar instruction set. It's pretty bad. So why not put it in hardware? It's quite simple for us to do, and then we can have just one instruction instead of dozens. So here's a simple unit test which showed that we've added this and it actually worked. The second step was the multiply and accumulate. What we wanted to do was to do this pairs of multiplies and subtracts. So what we've had to do is add a special instruction. We call it FFT multiply and adds, but it's actually a multiply, add, and subtract. The offset into the vector is automatically added. I put this in, just to calculate that. Here's your multiply, and the thing. So it looks like the pseudocode that you can see in the Wikipedia page and the algorithms that you can find online. But this should get us, the similar sort of 4-to-1 reduction in the code size for doing this thing. But the next phase will be to add a remap system. We've got an equivalent of a matrix multiplier system where you can actually remap the array into 2D or even 3D things. But what we want to do is to do these loops here and this one here actually as a single instruction. So we would do a setup, some setup, and then you would literally you do one load with a bit reverse load, and follow it up with this remapping of the what would normally be array style loads. So we have a single instruction. I'm really not kidding. One single instruction, and it does the entire vectorized FFT in place. It's deeply significant because we should be able to get away with only about 25 instructions. I'm really saying you should see some of the hand optimized assembly for this online. It's awful because it has to use explicit SIMD and you have to use loop unrolling. 600 hand coded assembly instructions is not unusual. Now, the only thing that we've got about this is that we've got to watch out for is that the other aspect of this is that you you end up hitting the same cache lines, and so our ongoing research into this will be to make sure that the cache is designed so that it has multi-way cache tags, four-way set associative, to make sure that when the multiple FFTs are done, which are on a similar power of 2 boundary, they don't end up pushing data out of the level 1 cache. So that's where we are. just exploring, then taking the Craystar concept to its a modern take on it. One thing that unfortunately is very unfortunate is that the Craystar supercomputer vectors were done in an era where performance of computers was, compared to today, is that it looks rubbish. But that's completely forgetting that if you pull the concept forward into today's modern processing nodes and geometries, you end up with something that's absolutely staggering. I'm really not kidding. Literally orders of magnitude reduction in program size, which translates to an effectiveness of the instructions. So thank you very much.